Okay, today we study Fourier integral and the Fourier integral theorem. Firstly, we consider the complex form or exponential form of Fourier series. We know that a 2-pi periodic function f can be expanded by Fourier series, a half of a0 plus sigma n from 1 to infinity an cosine nx plus bn sine nx. And because cosine nx, we know that cosine nx maybe can be written by einx plus e minus inx divided by 2, and the sine nx can also be written by einx minus e minus inx divided by 2I. So using this, if we defined alpha n to be an minus ibn divided by 2, and the beta n is the an plus ibn divided by 2. Using this alpha n and beta n, our Fourier series can be written by fx is half of a0 plus n from 1 alpha n e inx plus beta n e minus inx. Here alpha and beta n are given here, and if we denote alpha minus n, alpha minus n to be beta n. Okay, then all the alpha n can be written by 1 over 2 pi, 0 to 2 pi, or minus pi to pi, ft exponential of minus int dt. This is true for all an integer number. Okay, then the Fourier series can be written by the sum of minus infinity to infinity alpha n exponential of inx. Easy computation. Okay, so this is the exponential or complex form of Fourier series. That is, instead of using sine and cosine, we use the einx. Using this einx integers, you can see that this is orthogonal system. Okay, and this is for 2-pi periodic function. If the function is not 2-pi periodic, if f is p periodics, that is f is integral over 0p and extended as a p periodic function, extend to R as p periodic. Then similar to the 2-pi periodic case, we have fx is half of a0 plus sum n from 1 an cosine 2-pi over p nx plus bn sine 2-pi nx over p. Then we can also write this in the complex form, that is n from minus infinity, as the 2-pi periodic case, alpha n exponential of 2-pi nx over p I. Here alpha n is given by the integral, similar to the previous 2-pi case alpha n, that is 0 to p f t exponential of minus 2 pi n I x over p dt. Okay, this is just an elementary computation. So these are the complex form of Fourier series. Okay, complex form, very useful. Now we go back to our main topic, the Fourier integral theorem. So we introduce Fourier integral. Assume that f is a integrable function defined in this interval of length 2L and extended to 2L periodic. Extended 2L periodic to R. Okay, then we know that under some condition, the Fourier series of fx will converge to itself. So we might write plus sum of n from 1, then an cosine n pi l x plus bn sine n pi l x. Here the a n bn, we have formula for a n bn. A n is 1 over L minus L to L f t cosine L n pi t dt. And for Bn, this is sine. Okay, we have the formula for a n bn. Substituting this formula for a n bn into this Fourier expansion, we see that this equals 2L minus L to L f t dt plus the sum of 1 over L minus L to L. Substituting the a n bn expression here, and we have that is ft, the common ft we write separately, then cosine ln pi x cosine ln pi t plus sine ln pi x sine ln pi t dt. Here the integral of ft, which cosine ln pi t, give us an. Similarly, this integral which sine ln pi t give us bn. Now we can apply the formula for this expression. Trigonometric formula for this. We know that this can be written by 2L minus L to L f t dt plus the sum n from 1 over L minus L to L f t cosine L n pi x minus t dt. This is for 2L periodic function. Now let L goes to infinity. Remember that no periodic function can be considered as a periodic function which periodic infinity. Okay, so we let L goes to infinity so that we can treat the usual function not necessarily periodic. So the let L goes to infinity, we can write f(x) is how to say, this term. For this term, let's have a look on this. This is a sum L so this Yes. Sorry. Here the first term here, the first term, because f is integrable. F is integrable. Our basic assumption is that we consider the integrable function. For L, for f integral over R. Therefore, when L goes to infinity, the first term in the expansion, the integral of f from L minus L to L, that is minus infinity to infinity f, is a bounded quantity. And the L in the denominator make this term infinitesimal small. Okay, so this gives us a very small term, plus the later term will rewritten in another form, n from 1 to infinity, L pi, then minus LL ft cosine ln pi x minus t dt. Okay, so this can be considered as divided make some partition of the real line. This is the real line. We make some partition. So the point is L pi 2 pi L. The length of the partition, that is the distance from the these 2 points, this is pi over L. Therefore, this can be considered as the value of this function. Can be considered as value of this function. Value of this function, which is as a new quantity. That is value of this function, denoted by what? By phi lambda equal minus LL ft cosine lambda x minus t dt. Okay, so this is a function of L of lambda. Now, this sum, this infinite sum, can be considered as the value of this phi lambda at the point L n pi. That is the partition point we chosen. Multiplying the length of the interval, that is pi over L, then sum up. So roughly speaking, this is an integral. Okay, therefore this should be when L goes to infinity, the partition becomes finer and finer. Eventually the sum becomes an integral. Intuitively, this is not a legal mathematical reasoning, but it is very inspiring, so that we can guess or discover a new result. Okay, so this will goes to what? Goes to 1 over pi. This sum become integral from 0 to infinity. For our L from 0 to infinity, d lambda minus infinity, positive infinity, ft cosine lambda x minus t dt. Okay, we expect to have this result. Okay, intuitively, consider this like some kind of integral sum, Riemann sum. That is to say, we expect that under suitable condition, we will have fx equal 1 over pi 0 infinity d lambda minus infinity, positive infinity, ft cosine lambda x minus t dt. This is just the Fourier integral of f. We will prove this in the next video. Before that, we introduce a useful concept, the so-called bounded variation function. G defined in the interval is of bounded variation, denoted by G belongs to BVAB. That is, we use BVAB to denote the set of all bounded variation functions over the interval AB. What is bounded variation? If this function can be written by the difference of two increasing functions, if for f and g increasing function, that is the difference of two increasing functions is what we call the bounded variation function. But why this kind of function is called bounded variation? We will not go to the detail here. It depends on a partition of the interval AB and some condition. That condition is not very obvious related to the expression that G is the difference of two increasing functions. In the later course, in the future, the real analysis course, maybe you will encounter and study bounded variation functions seriously. Okay.